Hi, my name is Sophia Afric, and I'm coming to you from New York City to talk about Section 10.5, Graph Theory. So if we're going to talk about graph theory, first we have to understand what is a directed graph. A directed graph consists of a finite set of elements, or vertices, and a finite collection of ordered pairs of elements, or directed edges. So let's draw a quick directed graph. We have P1, P2, and P3 are three vertices, and then we have directed edges. So P1 points to P2, P2 points to P3, but P3 also points to P2, and there's no connection between P1 and P3. So then we have, in terms of notation, P1 points to P2, and P2 points to P3, which also connects to P2. Note that a point can't connect to itself, but 2 points can connect in both directions. So you might be asking, what does all this have to do with linear algebra? That's where the vertex matrix comes in. So we can use a vertex matrix to represent any directed graph. If the graph has n vertices, it's going to be an n by n matrix, and for each entry, if the directed edge exists, you put a 1, otherwise put a 0. The matrix will be all 1s and 0s with all 0s on the diagonal because a vertex can't point to itself. For our first example, let's look at flights between 4 cities. The possible flights are listed below. Let's visualize with a directed graph. From 1, we can go to 2, 3, or 4. From 2, we can go to 1. From 3, we can go to 1, 2, or 4. And finally, from 4, we can go to 1, 2, or 3. Let's fill in our vertex matrix. You can't go from 1 to itself, so we put a 0, but you can travel from 1 to 2, 3, or 4, so we fill those in with 1s. The rest of the matrix is as follows. If you wanted to travel from 2 to 1, you could do so directly. This is called a one-step connection. However, if you wanted to travel from 2 to 3, for example, you would need at least 2 steps. For example, you could go from 2 to 1 to 3. We want to figure out how many R-step connections there are between any two cities. This brings us to Theorem 10.5.1. Theorem 10.5.1 says the following. If we want to find the number of R-step connections from Pi to Pj, we raise matrix M to the R, and then the entry at Ij of that matrix is equal to the number of connections. Let's prove this theorem with the two-step example. Using what we know about matrix multiplication, we can generalize the entry at Ij of M squared. Let's take a look at the first term on its own. If mi1 equals m1j equals 1, there's a two-step connection through P1. However, if either of these terms is 0, there is no two-step connection through P1. So if there is a two-step connection here, this term is going to be 1. The same is true for every other term, so that the entry ends up being the total number of two-step connections. A similar argument stands for higher step connections. Going back to our flight example, how many two-step connections can we find from city 2 to city 3? Our first step is going to be to find m squared. Now that we have m squared, let's apply the theorem. If we look at the term in the second row and the third column of m squared, it's 1. So there's one two-step connection from city 2 to city 3. And by just looking at the possible flights, we can confirm this. The only two-step connection from 2 to 3 would be from 2 through 1 to 3. Our next topic is cliques. Cliques are subsets of vertices within a graph that satisfy 3 conditions. 1, the subset contains at least 3 vertices. 2, for each pair of vertices in the subset, Pi points to Pj and Pj points to Pi. And 3, the subset is as large as possible, so if you added another vertex, it shouldn't satisfy condition 2. Looking back again to our flight example, if we have a clique within our cities, that means that there is a direct flight from any city in a clique to any other city in the clique. But how can we identify a clique? In order to identify cliques, we define a new matrix S. The entries are 1 if Pi and Pj connect in both ways, or 0 otherwise. This means that any edge with only one arrow is basically deleted. This brings us to Theorem 10.5.2, which states that Pi belongs to a clique if and only if the I term of S cubed is not 0. Here's a justification for that. This term not being zero means that there is at least one three-step connection from pi to itself, and we can define this as pi to pj to pk to pi. And we know based on the nature of S that all these connections are two-way, which means that pi, pj, and pk are either a clique or a subset of a clique. What this means is that pi must be part of a clique. Let's apply this new theorem to our flights example to see if there are any cliques within our 4 cities. Let's start to fill in S. Because we can't go from 1 to itself, that's a 0. We can go from 1 to 2 and 2 to 1, so that's a 1. We can go from 1 to 3 and 3 to 1, 1. We can go from 1 to 4 and 4 to 1, 1. Now let's move on to the second row. We can go from 2 to 1 and 1 to 2, 1. We cannot go from 2 to itself. We can't go from 2 to 3 and 3 to 2, so that's a 0. And we can't go from 2 to 4 and 4 to 2, so that's also a 0. So now that we've finished filling out S and found S cubed, we want to say where is the II entry not equal to 0. And for this we want to look at the diagonal. And we can tell that SII, when it's cubed, does not equal 0 when I equals 1, 3, and 4. This means that cities 1, 3, and 4 are all part of a clique, and it turns out to be the same clique if we look at the conditions. Let's move on to our next topic, dominance-directed graphs. A dominance-directed graph is a directed graph with the following special property. For each pair of vertices, pi and pj, either pi dominates pj or pj dominates pi. However, both cannot be true. This is sometimes called a tournament because when we think about a round-robin tournament where every team plays every other team, each team must either beat or lose to every other team. Theorem 10.5.3 tells us that in any dominance-directed graph, there is at least one vertex from which there is a one-step or two-step connection to any other vertex. We call this vertex the most powerful vertex, but the question is, how can we calculate the power of each vertex? The power of pi is the number of one-step connections from pi plus the number of two-step connections from pi. Therefore, the power of pi is the sum of elements in the ith row of A, which can be found by adding the matrix M to the matrix M squared. In other words, in order to find the power of pi, you want to add all the elements in the ith row of M to all the elements in the ith row of M squared. For our second example, let's look at a round-robin basketball tournament with 5 teams, A through E. The results of each game are given. Let's visualize the tournament. A beat B and E, B beat C, D, and E, C beat A and D, D beat A and E, and finally E beat C. We can now see that this is a dominance-directed graph because every pair of vertices is connected in just one direction. Let's calculate power rankings for our 5 teams in the tournament. First, we calculate M based on our connections, and from there, we calculate M squared. So using our equation for power, we want to find the power of Team A. In order to do this, we add all of the elements in the first row of M and all of the elements in the first row of M squared. This gives us a power of 6. We continue and do the same process for teams B through E, and we get B has a power of 8, C has a power of 6, D has a power of 5, and E has a power of 3. So for our official power rankings, we have Team B in first, then we have teams A and C are tied, followed by D, and finally by E. If we look back to Theorem 10.5.3, we know that in any dominance-directed graph, there is at least one vertex from which there is a one-step or two-step connection to any other vertex. This is the most powerful vertex. In the context of this problem, B is the most powerful vertex. This means that if we look at any other team, B has either beat this team or beat a team that has beat this team. Before I finish, I just want to say thank you so much for watching my video. There are so many cool examples that I didn't have time to get to, but I hope that this proved to be a good introduction to graph theory. Thank you so much for watching, and thanks for a great semester.